Welcome to a homework walkthrough video. This is for Mechanics of Materials Fundamental Problem F12-16. And this, excuse me, this is from Dunway College of Technology, and this is the course MENG2240 Mechanics of Materials. So we're given this beam, and we're asked to find the reaction at roller B. We're told that EI is constant, so that's some good news for us. So as we look at this beam, what do we have going on? At C, we get two reactions. At B, we get one reaction. So far, so good. Oh, and now at A, we get one more reaction. So this is, we have four reactions. It's all coplanar, so we can write three equations of equilibrium. So we're first degree indeterminate. We're going to use the method of superposition here. So I'm going to choose to use this, get rid of this guy here as my, call this my redundant. So I'm going to end up with my primary beam. It's going to be this guy, CY. CX, AY, apply this moment, MO. So we look at that beam, what we're trying to find is our deflection. So what is our elastic curve going to look like? Well, I'd expect it to look something like something of that sort. And if we turn back to Appendix C, we should be able to find a type of deflection or elastic curve equation for this type of thing. So it's a simply supported beam, right? We have a pin over here, a roller there, and we have an applied moment at one end. So this is like beam 3 of the simply supported. And we have, it's kind of the inverse of this guy, so we're going to have our deflection here is V. It's going to be negative M0x over 6EIL. And L in the diagram is the whole thing. And that is going to be multiplied by, I'm going to try, suddenly lost my cursor, there we go. L squared minus x squared, where we care about what position we're at. So that's what we've got. It's we've got essentially the mirror of that, but we can use that same equation. So as we look at that beam, what do we have going on here? So our moment is there. L is going to end up is really going to be 2L because we have 1L, 2L. So we're going to sub 2L into each of these locations. X is just going to be 1L at B. So as we sub those in, our deflection at B is going to be our moment times our distance over 6EI L times 2L, there we go, times 2L is going in there, so we'll get 4L squared minus L squared. And so as we reduce that down, and I'm showing that this is down here, so maybe I should put a negative sign there, keeping that through. So I'm going to find negative. So I carry this through here. One of these L's are going to cancel out. I'm going to get 12. Over here I'm going to get 3. So that's going to be a 4 on the bottom. EI on the bottom. And on the top I get M not L squared over 4EI. So that's going to be my deflection at that point. So that's our primary beam. My redundant now. What am I going to do for that guy? I'm going to get rid of my applied load. So I have my AY is still here. I'm going to have a pin connection here. I still have CY, CX. I got rid of this guy. This one here is 0 in this case. And now I'm going to push up on this beam BY. So we're going to look for what this, and maybe I should put a subscript 1 on this one here. It's our first deflection, now our second deflection. So in this case, we're pushing right in the middle of the beam. Our deflection here is that first case from the Appendix C. Supported. In this case, we have, it's going to be our max deflection is right at that point, so we're V max is negative PL cubed over 48 EI. L is going to be 2L, right? We're going to sub 2L into that guy. So our deflection from that is going to be BY is our P. So we're going to have negative BY because it's going in the diagram P was down. So we're going up, so we're going to have a positive BY. L cubed is going to be 2L cubed. It's going to go over 48 EI. So that transforms into BY 8L cubed over 48 EI. It goes to BY L cubed over 6 EI. Now what do we know about these deflections? So that's going to be VB2. We know that VB1 plus VB2 has to be 0, right? So we go back to our original beam. We have a pin here. So we need to have our total deflection to be 0 at that point. So I'm going to set those equal to 0 here. So I have one positive. This guy was negative. So I'm going to be solving in terms of BY, solving for BY in terms of M0, L, EI, etc. So what do I have? I have negative M0 L squared over 4 EI plus BY L cubed over 6 EI equals 0. So I can multiply by EI on both sides. That gets rid of those. Divide both sides by L squared, so I get negative M0 over 4 plus BY L over 6 is 0. So solving for BY now. So I'm going to get multiply this side by 6, divide by L. Just take the inverse of that. Pull this to the other side, I get positive M0 over 4. This is an L, not a 2. And so as I carry that through, what do I get? BY, I get 3M0 over 2L. And that's our answer. So looking back, what did we do? We picked a primary beam. In this case, I pulled out B, my support at B as my redundant. I just analyzed a simply supported beam with a moment applied at one end. Found that deflection curve from Appendix C. Found my deflection at the point I was caring about. Came back, removed the first applied load, put in my reaction as a load. Found the deflection from that. Added those two together to be 0. This is our compatibility. And as a result, we can solve for BY in terms of our other variables, and we found it here to be 3M0 over 2L.